A stochastic vector is, as we will see later, in system theory, is often called a state vector. It's the state of the system. If we know the state of the system, we can use that as an initial condition to forecast what will happen in the future if we know the forcing. So this is why it's called state estimation. We never know the state exactly because it's a stochastic vector, but given the observations that we have until then, we can get an optimal estimation with the smallest error possible given the observations that we had until that time. And that's why it's called state estimation. Data assimilation is a more modern term. That is when you have a model and observations. The model gives you an initial estimate of the state with the associated errors. Then you take the observations and you weigh them optimally. So you ingest the observations into your model state estimate, and that's often called data assimilation. A Kalman filter is one of the data assimilation methods we're going to talk about in this specific introductory lecture to data assimilation. But if you go to more advanced courses on data assimilation, which is not part of our course, but you will see that there are different type of much more complicated, both recursive but also so-called batch data assimilation algorithms. Well, like I said, the linear Kalman filter is one of the most basic ones, and we're going to investigate that in this series of lectures. Okay, just starting actually with this very simple example. If we have two sources of information, so two estimates of the unknown state, x, yeah, so let's call it x0, yeah, and xi, and both are subject to error. So this one has an error and this one has an error, and the errors, this E0 and EI are standard Gaussian random variables, and sigma naught and sigma I are the respective variances. In this case, you can see, or standard deviations, that the standard deviation, the green one, sigma I, is a little bit larger than sigma 0, the red one. And then the blue one is an optimal combination of both types of information. And you can see the optimal estimation, the optimal prediction is a weighted average of x0 and xi, where the weights are based on the ratio of the variances. So this is the variance of I divided by the sum of the variances, and the variance of O by the sum of the variances. Yeah. So the larger the variances of I, yeah, compared to the variance of O, the more this one gets a weight, yeah, and also the inverse. If the variance of x0 is very large, then you can see that this one gets more weight. Actually, you can also see that in the limit, suppose that the variance of I is infinitely large, yeah, you get infinite divided by infinite, which is 1. So xn will be equal to x0, because the green information doesn't end anything. It has an infinitely large variance. Yeah. Also the other way around, if the variance of x0 is infinitely large, then we get again that the optimal prediction is entirely equal to the a priori prediction xy. And of course, if the variances are equally large, you can see that they get half the weight. Yeah, so it's an exactly unweighted average of the both. Yeah, so we can start playing around. And by the way, this is the total variance. As you can see, the total variance depends on the individual variances. Yeah, so if the variances of I and 0 are both larger, the variance of the total, the uncertainty about the weighted average increases as well. Yeah? And you can actually prove that the variance of the result, sigma n squared, is always smaller and equal than the individual variances. It's an HTML file that you can start, you double click it, and then some browser opens. For instance, suppose that we increase the variance of the second one, of the green one, xi. Let's do that. Let's increase the variance. And you can see what happens. The optimal prediction slowly goes to the variance of to the one that to the red one, yeah, x0. Or the other way around. If this variance is going to be very small, you see that the variance is gonna go close to the green one. Yeah. And if the variances are equally large, approximately, you can see that it's somewhere in between the two. Yeah. Okay. So let's move on. So this is actually the very most simple form of what we call the Kalman filter. You have two types of information that you combine in an optimal way to get a new prediction that is better than each of the individual predictions. This is still visible, the next one?
Yeah, we can see it.
Okay. So now we're going to go and add the dynamics. Suppose we have the following example. We have a groundwater depth below the surface, yeah? We have evapotranspiration and precipitation that we have a time series of. And every 2 weeks we observe, or every so many time steps, we observe what the water table depth is, or the groundwater, or the depth below the surface, or the water table elevation. Yeah. And what we want to do is we want to predict what happens in between and also do a forecast with it. So let's go ahead and do that. So to do that, we build a very simple transfer function noise model. We saw that in chapter 6. This is a very simple transfer function noise model with one autoregressive part. So Z at a certain time, which could be water table depth or water table elevation, depends on the average water table elevation C plus delta times ZT minus 1 minus C. Yeah. So you can see we first subtract the mean before we apply this transfer function noise model. It has one exogenous moving average term, which is, in this case, we take precipitation and we subtract evapotranspiration. Maybe it could also be potential evapotranspiration as a proxy. So that's U. And then we have some noise. Yeah. So this is nothing more than a transfer function noise model. Okay. Now, usually this noise is modeled by an ARMA model, but let's suppose that this is such a good transfer function that the residuals to that function can actually be assumed to be white noise. So we cannot, so all the information that we can has been extracted from this particular transfer model. So we assume that it's white noise. Yeah? So the expected value, so discrete white noise in this case. So the expected value of W is 0, and the expected value of WT plus K is 0 if is equal to the variance of the white noise if K is equal to 0, but it's not correlated in time, as you can see, because if K is other and something else than 0, 1, 2, minus 1, you can see there's no correlation. Yeah? So this is discrete white noise, not correlated in time, with a variance equal to to sigma W squared. Yeah. So this is a simple discrete And we can use this to interpolate or predict forward in time what the water table is going to be. Now, at a certain time, we also can have an observation of Z. Now, this observation is not without error. If you measure a groundwater level with a traditional apparatus, you have this little piece of metal which is hollow inside. It's connected to a tape measure. You just let it slide into the tube until you hear a plop. Bloop, bloop. That is when you hit the water table level, and then you measure from the tape what the depth is of the water table. That is how it's traditionally done, and then the error would be on the order of 1 to 2 millimeters, something like that. But even if you use a pressure transducer, you would have maybe half a centimeter measurement error from there. And we also assume that this is white noise. So the measurement error is white noise as well. So expected value is 0. If I take two subsequent measurements in time, those errors are not correlated, as you can see. So we know the variance of this residual here from our transfer model, and we also know what the variance of our measurement device is. And we can safely assume that the error that we make in our measurement is completely uncorrelated, not dependent on the error that we make in our model, because they are basically not connected whatsoever. So these are the ingredients that we have. Now, we take the screen at the build, the Netherlands. There's one that actually measures every day. But we assume that we have daily measurements there, but we assume that we have only traditional bi-monthly measurements that we usually have, for instance. Then we fit this transfer model here, this part. So we get a delta of 0.94. So with a daily time step, omega of 0.56. And the average depth is minus 130 centimeters. We assume that we get the residuals. The residuals, we can calculate the variance of the residuals. If we apply this to our observations, and we get a standard deviation of 3.35 centimeter. And we assume a rather large, but just for a matter of explanation, measurement error, standard deviation of 1 centimeter. And every 15 days on average, we measure, we take observations. Yeah. Now we're going to devise an optimal weighting scheme. So this would be a forecast. Suppose that we have suppose that we have an optimal prediction. So we have two types of superscripts here. One is a Z bar. So the bar means this is an optimal prediction given all the observations that we had until the previous time. So not observations taken at ZT. So this is an optimal prediction here. And this is also an optimal prediction, but this is including all the observations that we had until ZT minus 1. This is often called the time update, and this is called the measurement update. I'm just giving you the terms already. But suppose we do a one step ahead prediction. Z bar is equal to C plus delta Z hat, T minus 1, plus the precipitation and P minus T, E for that in that specific interval. Now, we do a forecast. We can also compute what the forecasting error is. Actually, this is the variance of the forecast at time t. F stands for forecast, and U stands for update. So after we updated with the observations. So suppose that this is the so-called measurement update, and this is the variance of the measurement update. Suppose that we know that from already, then you can actually work out. You have to just take it from me that the variance of the forecast is equal to delta squared times the variance of the time update of the previous time step plus an additional error that we get from the model. Yeah? So this is the forecasted variance. Now, suppose that at time t we have an observation. Yeah. Then we can calculate the weight in the similar fashion as we showed before, because we have two types of information. We have measurements at time t, and we have this time update, zt. And what are the weights? Well, this is one weight. The weight that is attached to this guy here, that is the variance. Sorry, so this is the weight attached to the measurement. Sorry, yeah. This is the weight that is attached to the variance. So to the measurement. That is the variance of the forecast divided by the sum of the variance of the forecast and the measurement. So the sum of both, the variance of both sources of information. And then, of course, these weights have to add up to 1. So 1 minus this guy here is equal to the variance of V divided by this one. So we calculated the weights, and then the optimal one would be, so this is the weight that we attach to the observation, as we can see like this. And this is the weight that we observe, of that we attach to the model prediction. So, and that's also logical, because if this is a very uncertain model prediction, sigma, the forecasting variance is extremely large, yeah. Then this one would be equal to 1, and this one would be 1 minus kt would be 0. So we would say that the optimal prediction at time t, what's also called the time update, including all the observations that we have until time t, would be exactly equal to the observation, or the other way around. Suppose that we have an extremely useless measurement, so the variance of the measurement error would be equal to infinity. Then we basically get that this weight becomes 1 and this weight becomes 0. So we say that our optimal prediction at time t would be exactly equal. We would take that equal to the time update, so to the model prediction. Now, we can also update the prediction error variance. We use the same formula that we saw in the HTML example of the two examples. So it's the product of the variances divided by the sum of the variances. And actually you can work out that this thing is equal to 1 minus kt times the variance of the forecast. You can see that because 1 minus k at time t is this guy here. So this guy times this one, that's exactly what this is. So the variance of the update of time t is 1 minus kt. Now, in case we do not have a measurement at time t plus 1, then we simply set that, oops, there's an error here. Let me see if we can change this. So, in case we have no measurements, still have an error here. Let's see, this is all work in progress, guys. In case there's no measurements, then the optimal prediction at time t is equal to the model prediction. Yeah, so we don't have any update, and the variance therefore necessarily is equal to the forecasting variances. Yeah. Now, if we take these equations all together, This is what we call the Kalman filter equations. In this case, for a so-called scalar example. So we have a single stochastic variable that, so we know, so in this case, a time series of one single stochastic variable that changes over time. So we have the forecasting equation, we have the forecast error variance, we calculate the weights, that gives us the so-called Kalman gain, KT, and then we get an update which is equal to the model prediction plus Kalman gain times the difference between the observation and the model prediction. And then we get the updated variance, which is always smaller or equal than the forecasted variance, which is 1 minus KT times the forecasting variance. Yeah? So these are the Kalman filter equations for a single valued, a scalar example. So what we get is every time we do a model prediction with our model, if we have an observation, we update that prediction with this observation. And what we typically do is we take an optimal weighted average, depending on the relative accuracies of both sources of information, the model prediction and the observation, and we take a weighted average of the both to get an improved prediction or time update whose uncertainty is always smaller or equal than the one of the forecast. Now this is what we see, for instance. This is when we do not do the updating. That's so we're only using this part of the model and we forget about the rest. Then this is we get these are the predictions, these are the observations, and these are the innovations. And if we do an update every 15 days, we can see that we're doing better. Yeah. So whenever we have an observation, we update the model prediction and get a better initial condition also for the next forecast, and therefore our forecasts are also more accurate. Now, if we update every so many days, you can actually see that there are also in this case we have every 2 weeks we do an update. What you can see is that the prediction error, this is the standard, this is basically the standard, this is the standard deviation of the measurement update. And we can see that after a measurement update, it's very small. It's smaller actually than the 0.5 millimeters or 0.5 centimeters that we had from the measurement. We can see that it gradually goes up when we start predicting ahead in time until we get the next observation, and then it goes down again. And that repeats itself. In this case, we see that there are certain periods that we don't have any observation. For instance, here we miss one observation and here we miss 2 observations, and you can see that the variance becomes higher even. Yeah? So this typical sawtooth variation of the standard deviation of the measurement update is typically what you get if you apply a Kalman filter. Now, let's. What actually is interesting is if we now start to compare what we do, how this variance, how this uncertainty develops over time. How do we this so-called sawtooth can be described by seeing what happens, how this error accumulates over time if you don't do any update. And this is actually akin to what we saw with time series modeling. Now, what we saw here is a so-called autoregressive over transfer function model, a special type, which is called an autoregressive exogenous variable model, or ARX model. It's basically a transfer function model with only a single autoregressive and a single input. And suppose that we start predicting ahead in time, and we know at time t, we know exactly what the state is. Just for, you know, just for an academic exercise. So suppose that we have a very good observation apparatus and we measure exactly the state at t0. We know exactly what it is, so the variance is 0. Yeah. Now we forecast one time step ahead in time. So if we go back to our equations, yeah. So then the error, the forecasting error would, of course, because this one would be 0. So the forecasting error would of one time step ahead would be exactly equal to the variance of the model error, yeah? Sigma W squared. So one step ahead would be equal to that. Then two step ahead, we don't do any update and we do another step ahead. Yeah. Then applying that equation, sigma squared ft plus 2 would be delta squared ft plus 1 plus sigma w, another one. But of course, since we do not we're not doing any time update, yeah. So as we see in our equation originally, this one should be the variance of the update. But of course, the variance of the update is equal to the forecast if you don't do any observations. So what we get is two steps ahead. We get the variance of the update of t plus 1 is the same as the variance of the forecast at t plus 1. So that's this one. And therefore, we can substitute this guy here, and we get sigma squared t plus 2 is delta squared sigma w squared plus the sigma w squared. Now, what about 3 time steps ahead? We get this guy here. Yeah? So you get this geometric series of deltas with the variance of the model error. And many time steps ahead, you can actually see that we get this one. And this is a geometric series that in the limit is equal to this one. Yeah. Now this is, we already saw this actually, because we all and of course if k becomes infinite, yeah. So if k is infinite, we get something that is smaller than 1 to the power of minus infinity. So this one becomes 0, and we end up with that in infinity. This one becomes equal to the variance of the noise of the model error divided by 1 minus delta squared. And you can see the larger the delta is, so the more correlated in time the groundwater levels are, or the errors in the groundwater levels are actually, and the groundwater levels itself are, the larger the variance and the infinity. So the more it is important that you do the updating now and then, yeah? Because it basically rises exponentially to a very high value. And these two are recognizable because we already saw that if we use an AR1 model to forecast ahead, and remember in time series modeling we always know, if we did the forecasting, we assumed that we knew exactly at t0 or at the current time what the state was, what the value was. Then actually, if you assume that and you apply it to a Kalman filter, you can see that the Kalman filter, and you do not do any updating, then the Kalman filter is actually equivalent to a forecasting with an AR1 process. Yeah. So that's what you see. So what do we need to remember from this? The Kalman filter is when you have observations that are in error and you have a model that is in error. These errors are independent in time and they are independent of each other. Then every time you have an observation, you can update the state to get the best possible prediction of the state. which also makes your forecast better then again, because you have better initial conditions for your following forecast. The problem though, that is what a Kalman filter does. Of course, in time series forecasting, we often assume that we know we don't have any observation errors, but we also do not have any updating, and therefore the forecasts, if when applied to a Kalman filter, look like this. Okay, so we can also do this graphically. Suppose that we have the optimal prediction at t-1 from application of the previous Kalman filter in the previous time steps. Then we use our model to do a model update or time update. Then we have an observation that may be different, so we update the time update of our model to a weighted average of this one based on the respective forecasting variance and the variance of the measurement error, and that is used for the new time update. Yeah, and this is how it goes. So in this case we saw that we do not have any observation, so we use the time update is equal to the measurement update is the same as the time update, and then that is used as initial condition for the next time step. Here we do have an observation, and we can see that we are updating it. And this is called the measurement update. Now, if we wouldn't have any measurements here, then this would typically be the open loop, so without any updating. Okay, so this is what the Kalman filter does. It optimally weighs model predictions with observations whenever they come available. So if we would make a sort of more anecdotic example of a Kalman problem setting, is that you have some simple model. You have some information where you are. You have other information. You want to reach this road here, yeah, and you have at the dotted line, so you can go home. You're on a survival trip. You don't have a GPS, but you do have a map. So counting the paces or the hours walking from where you started, you know more or less where you are with certain error compared to the road. But you also know from your map that the road is you see the wood ahead of you, and you also know that this road is a certain distance from the wood. So you have two types of information. You have a model prediction. You have an observation. So how can we compare both those to know, to say how far you exactly are away from the road, and which way should you go to reach the road as quickly as possible? That's the Kalman problem. Now, before we go there, the Kalman problem we have to and apply it. We have to make a distinction between so-called static systems and dynamic systems. Yeah. So in a static system, we have a state vector, yeah, Z1 to Zn, that consists of variables that are not changing in time. Yeah. For instance, the vector of soil moisture content of a given time, so we're only interested in a given time of multiple layers, or the groundwater or the soil moisture on a grid at a certain time. So time is not an issue here. We're only interested in the status or it could be, for instance, hydraulic conductivity at multiple locations in the field. Could be a state vector. If you put them in a vector, it's called a state vector, and those systems do not change. And we have also a static set of observations, only one set of observations, and we want to combine both sets of information. Yeah. That becomes different if we have a so-called state vector in time, like we saw before. Suppose this is the groundwater level at multiple locations over time. And then also observations can be taken at different time steps, right? And a state space formulation is what you get if you have multiple variables that you want to consider jointly, and you put them in a so-called state vector, in a vector. And that's a state space formulation. So the Kalman filter is actually mostly is about this so-called dynamic state space formulation, but we will see that actually the principles of the Kalman filter can also be translated to a static system, which I'll show you in the next lecture. So let's move to the formulation of the Kalman filter, because previously we looked at the Kalman filter only for a single value, a scalar, but now we're going to look we're going to extend the Kalman filter to a state space where we have at least two different variables that we jointly want to trace in time. Now for this we take this very simple example of two connected vessels that have an outflow point on both sides. They also have inflow point. They also are mutually connected. So if this one is higher than this one, it not only loses water to this side, but also to the other vessel. And they both have water poured into it. With that water that's poured in it can be fixed, but also changing over time. Yeah. So in our case, we assume it's fixed. Yeah. Now we have two variables. That is the volume of water in the left and the volume of water in the right. And we want to estimate those at every time step. Now it's difficult to get that volume. We have to estimate it. We can, and we use a model to do that. We assume that these are capillary tubes. So there's a simple linear relationship between, say, the volume and the outflow. Yeah. So if we want to so this upper equation gives the water balance of the left vessel. So the volume in the left vessel, in the left vessel, or T+1, is equal to the volume it had in the previous time step, minus the outflow on this side, plus the possible inflow from this vessel, but only if the level in this vessel, the volume, is higher than in this one. Yeah. Plus the inflow. The same for this one. So we can take these together. We have two water balance equations for these connected vessels. And we can put them in a matrix vector notation. And that's called the state space formulation. So we have ZL T+1, ZR T+1, and we can factorize ZL and ZR from these equations. We see that it's a matrix multiplication of this system matrix A times the state vector at the previous time step plus the input. Yeah. So if we put that in a state equation, so this is the state equation. If we put that in matrix vector notation, we have Z at T+1 is A times ZT plus the input U at T+1. Now, we can also estimate the volumes, measure the volumes, yeah, by, if we know what this area is, and we know what the elevation is, we can try to estimate with a very simple approximation what the relationship between measuring the height and the volume. And the height is nothing more than the volume divided by the area that we have. So if we measure, so suppose this area is assumed to be constant, then if we measure the depth, we also have an idea of what the volume is. Of course, there's an error here, and we can assume that both, this is called the measurement equation. So what we can then do is we have a so-called linear dynamic system, and what we do is we add noise, because we know that our model may be in error, because there may be small fluctuations. This thing may be not fully capillary. We do not know the constants exactly. We have estimated them, so there's always some measurement error here, or a model error, W. So we add to our state equation, system equation, model noise, and we add to our measurement equation, measurement noise. This is called the linear stochastic system. And dynamic, a linear dynamic stochastic system, because it also changes in time. Now you can already see this looks like a matrix vector version of the scalar groundwater example that we showed, where we derived the Kalman filter for. Now we have to assume that this noise is, so these are unbiased models and observations, so the expected value of the noise, the model noise, is 0, the expected value of the measurement noise is 0, the model noise is independent in time, the measurement noise is independent in time, and the measurement noise and the model noise are not correlated, not dependent as well. What you can see is that the expected value of Wt plus K, for K is equal to 0, even though it's not correlated in time. The error you make in this part can be correlated to the model that's made here, and that makes sense because they are connected, right, by the same parameter CL, CLR. So because of the connection between the two, if you make an error in CLR, it affects both the left and the right vessel. So it may be reasonable to assume that this is a covariance matrix that is also has the cross terms that are equal to non-zero. So there's a cross correlation between the noise here and the noise there, and vice versa. Probably not so for the measurement error. I think if we independently measure the height here and the height there, they're not likely being correlated. So this is probably a diagonal matrix with the variances of the same variance of the measurement, the same measurement variance, error variance at the diagonals, and zeros at the off diagonals. Now we can then apply this in the Kalman filter algorithm. Suppose that we know the initial conditions, and we also know that we know them with a certain error. This is the error covariance matrix of the initial conditions. Then we can do a prediction step. We can do a so-called, so this is my time update as it's called. So that's a one step ahead prediction. We can also compute the variance covariance matrix of the prediction error, which is the expected value of Z minus its unknown value and the covariance of that. And it's actually equal to this one here. Then we can compute the Kalman gain, which is a weighting matrix. Once we have the weighting matrix, and we have an observation, yeah, the observation Y, we can compute we have an update of the state by applying this updating equation, and we also get an updated covariance matrix of the measurement update error, as you can see here. And by the way, this thing P is smaller and equal than T at all times. Yeah. So we're always improving, but we're never getting worse if we ingest observations. Now note, this algorithm is a little bit more general than we usually use than we are going to use in our example, because what you can see here is that the system matrix A and B, as well as the covariances of the model error and the measurement error, can also change in time, as well as the model, the so-called model matrix. So H is also, so that links the time updates to the observations. That one is also can also change in time. But in the example we're using here, all these matrices are constant in time. So it's a little bit more simple than this most general Kalman filter algorithm. Some properties of the Kalman filter algorithm that are of interest. If the measurement noise and if the model error and the measurement noise are both multi-Gaussian, so their stochastic elements are jointly described by a Gaussian multivariate probability density function, then we can say that the optimal prediction of Z given all the observations until time t, so the time update, but also the measurement update, so that's the optimal prediction given all the observations until time t minus 1, both are also so-called maximum likelihood predictions. So if we ingest this in the conditional multivariate probability density function, we get the highest probability density possible. So this is called a maximum likelihood prediction. It also means that they are also, we can also derive the conditional densities Fz given all the observations until including time t minus 1, or the probability density of Z at t including all observations up to and including t itself. And they are multivariate Gaussian with Z with respectively mean and the covariance function. So this is the conditional mean, conditional covariance, conditional mean, conditional covariance. Yeah. And the reason is that if Wt and Vt are Gaussian, then and all the other things are linear combinations of that, then any optimal prediction Z should also be Gaussian, because it's a linear combination of those noises. And anything that is a linear combination of Gaussian is by itself Gaussian again. If Gaussianity cannot be assumed, then at least the measurement update and the time update are the best linear unbiased predictor. So they are unbiased and then minimizing the prediction error variance. So that at least you can say. Okay, so now let's move to more graphical representation on how the Kalman filter then works. So suppose that this is at time t, yeah. We know this is the initial, this is Z hat that we have. So so this is Z hat at time t. So this is the, so we see it's uncertain. And the uncertainty here is equal in both states. Yeah, so this is the uncertainty about ZR is the same as the uncertainty about ZL. In this case, we also have, just give you some examples. This is a case where we know the states, it's the same value same optimal prediction, but the uncertainty is much smaller. Yeah. In this case, the uncertainty in the right volume is much larger than in the left volume, for instance. And in this case, the errors in ZR and ZL are quite similar, but they are also correlated, as you can see. A larger error in Z also means a larger error in L. Sorry, an overestimation in R also means an overestimation in L. Yeah? So they are dependent. And in this case, by the way, the differences between ZR and ZL, ZR minus ZL is quite well known, but ZR and ZL itself are still quite uncertain. Now let's see how this works. So suppose at t minus 1, from a previous application of the Kalman filter or from some initial estimate using another method, we know the optimal prediction of Z t minus 1. This is this one. And we know its covariance matrix. Now, if we take the diagonal of the covariance matrix, we can make these, from the covariance matrix and the mean, we can make these lines of equal probability density from that, as you can see. So this is basically a projection of the bivariate Gaussian probability density function of Z at time t minus 1, given all the observations until that time, based on this mean and this covariance matrix. You see it's rather certain here. So this is going to then be used as to predict one time step ahead. So we know the input Q1 and Q2, and we can predict one time step ahead. You see, we end up here. So this is the new Z, this is the time, the model prediction at time t, without using any observations yet, only the initial conditions at t minus 1. And this is the associated uncertainty. So again, this is a multivariate, these are lines of equal probability density from a multivariate probability, from a Gaussian multivariate probability density function with mean equal to Z hat at time t and the covariance equal to m. Then we also get an observation at that time. This observation, of course, is different than we observe both R and L, maybe by measuring the water height, and we get an estimate of the volume with an estimation error, again assumed to be multivariate Gaussian. Yeah. So we see that we have a mean and a covariance of the time update and the measurement update, and we can bring them then together by calculating optimal weighting matrix and updating, getting an updated state with elements ZR and ZL that's somewhere in between, with a reduced or with a smaller probability, with a smaller uncertainty. Actually, the uncertainty here resulting, if you go back, you can see that the resulting uncertainty is smaller than the individual uncertainty of the model and the observations. Yeah. So this then is our new optimal prediction and a covariance, and of course they can then be used for the next time step. Yeah. By the way, this also works if we are not measuring both the left and the right vessels, but we're only measuring one of the vessels. Yeah. And that has to do with the fact that due to the dynamic interaction between the two vessels, as well as possible the off-diagonal elements of the measurement of the model noise W, so the matrix Q, which also have off-diagonals not equal to 0, these Z1 and ZR and ZL are dependent of each other. And because of the dependence, it's often feasible to only weigh one of the two and still get a better prediction.